Good morning, everyone. First, I would like to express our sincere gratitude to the organizer committee of CMMSE and CHPC 2026 for putting together such an excellent program and for the opportunity to present our work here in Kaddish and online. My name is Pakkapon Preechasilp from the program in Mathematics and Pibul Songkham Rajapat University, presenting on behalf of our team. This is our team from Innovation University and under the name Deep Math AI Research Group NU. So today I will present our work on AMSGNN. Adaptive Matrix Scale Gradient Network Neural Network for Convex Semidefinite Programming Problem. This work which I developed a Lyapunov-based convergent theory for a continuous time neural network that solve convex semidefinite programming with inequality constraint. Next. This is the roadmap of the talk. We start with the motivation and the formulate problem and write the AMSGNN dynamic. The core of this talk is the Lyapunov analysis, followed by 3 numerical experiments, and we close this talk with the conclusion and a summary of everything. So, why I study the semi-definite programming problem? Because convex semi-definite programming problem is a powerful model language. It extends linear and quadratic programming by adding a positive semi-definite constraint and as on a linear metric pencil. This single constraint captures an enormous variety of applications from control, design, and linear metric inequality to mechanics relaxation in combinatorics, geometric compression, robot optimization, and as well we will demonstrate quantum state estimation in our experiment. The standard numerical machinery for SDP is a measure like an interior point, augmented Lagrangian, splitting method. However, each iteration requires assembling and factoring a dense, often ill-conditioned KKT system. This limits their use the real-time or embedding setting. Our approach to take a different route. We reformulate this problem as a continuous time dynamic system. So this is the idea. So sorry, may I move this slide? Okay. The idea is using the continuous time neural network for optimization. Go back to the Hopfield and Tang in 1985. The key insight is simple. Is it a design and ODE whose equilibrium are exactly the optimal solution? The classical is gradient neural network. So integrate the KKT residue field direct using uniform scale again. In this case, this is alpha. This may be another symbol. It is elegant and work well when the problem is well conditioned, but when the SDP data is ill conditioned, as commonly occurs in the sum of square relaxation, the ODE becomes steep and the single scale again for the prohibitivity small integration steps. In the deep learning science community, solve an analogous problem with AMS-grad. Instead of scalar step size, maintain a coordinate y diagonal preconditioner that is a non-decreasing, tracking a running maximum of the square gradient per coordinate. Our contribution is to transplant this idea into the continuous time GNN for convex ACP with a completely abundant proof for global convergence. So this slide is the idea for relationship between the solution of our problem and the KKT condition. Our problem classes minimize the convex smooth objective subject to the linear metric inequality and smooth convex inequality constraint. The solution triple consists the primal variable and metric dual variable, and the inequality dual variable is the KKT point when the three conditions hold simultaneously. And the two projection quality do the heavy lift. The first projection is shift dual metric onto the positive semi-definite cone, and the second projects the shift inequality dual to the non-negative, or then that means is greater than or equal 0. The next slide is we define the KKT residue field with the three box corresponding to three KKT conditions that the previous slide. The X box encodes the generic condition. The Z box measures the semi-definite feasibility gap, and the U block measures the inequality feasibility gap. The crucial structure property, which we call the KKT relationship, we say the inner product between the current set error and the residue field is always non-positive, but that above by the non-negative feasibility measure. The inequality is the engine behind the entire Lyapunov analysis, and it also gives us that residue vanish if and only if the state of KKT point is a KKT point. So the next slide is the idea of the adaptive metric tracker. Now for the key innovation, the tracker is a low dimension vector with only n plus p and plus 1 component like this. It says sum is a Q symbol that track a non-decreasing upper and below of the square residue per coordinate. The tracker dynamics are governed by Kripke ordinary differential equation. The lower keep in for that the tracker never decreases. This is the continuous time analog of the AMS grad maximum tracker property. The upper keep each tracker component strictly below the prescribed maximum M. This is the prescribed maximum M. Guarantee that the preconditions say about it. From the tracker, we build the block diagonal precondition. Each diagonal entry is the reciprocal of the square root of the tracker value plus a small equalizer. As the tracker grows, corresponding step size shrink exactly the adapter damping we want. We use the single scalar tracker for the entire metric dual block because the sexual projection require isotropic scaling to commute with eigenvalue decomposition. That's why the dimension of this ODE is reduced to n plus p plus 1, not n plus p plus m squared. So the next slide. Combining everything, the AMS GNN is a coupled system. The state velocity equal a speed parameter, that is alpha, time the diagonal preconditioner dv, and time KKT residual dv, while a tracker involved by the Kripke ODE described before. Lemma 1. We confirm that three structure property the tracker monotone non-decreasing, but that between the initial point v0 and the cap that means the upper bound M, and the precondition satisfy uniformly spatial bound. And theorem 1 be exhibits that the equilibrium of AMS GNN are exactly with the KKT point. the probe screen. The important remark that the crypt acts on the metric target, not a set velocity itself. So the zero set of the velocity is identical to that the standard GNN. Next slide is we recall some neurodynamic that familiar to my neurodynamic. The classical one is gradient neural network GNN, which had a adaptive gain. A single gain as scalar alpha, and so the PNN projection neural network that also have a single gain alpha, and more recently Professor Jaha Chandri and Professor Wankari, they make the neural network that have something like adaptive gain, but they use I plus the Jacobian of G. That is different from our, because it's DV, we don't use the computation of the G. So the next slide is composite Lyapunov function. The Lyapunov function is the heart of our paper. We build the composite function from two ingredients. The first is a certain point residual potential whose gradient recovers 3 KKT residual block up to side. When we differentiate it along trajectory, we get the mix of the helpful and harmful term. The helpful is a primal block, but the harmful with for the metric and inequality dual block. The second is the adaptive inverse metric distance, a weight square distance from the current state to the KKT solution scaled by the exponential damping factor, something like this, that depends on the sum tracker value. This exponential damping is precise calibrate the neutralize the growth of the inverse metric at a tracker increasing under the simple lower bound on a damping parameter. Differentiating this term yield about involving only the inner product and set error of the residue, which we control by dissipativity inequality from the slide 6. The composite function is the sum of two ingredients that I said before, with a small positive weight with a time before. So the next slide is the main theorem. We have the theorem to the dissipation. Give the time derivative of the composite functional is bounded above by the negative weight. Sum of the square norm and all three residue blocks. So the functional is a strict decreasing whenever the system is not a KKT point. This is the key estimate from the everything else follow. Theorem 3 said the global existence. Because the composite function is non-decreasing and coercive in the state variable, every sublevel set is compact, so the trajectory cannot escape to the infinity. And theorem 4 give a Lyapunov stability, the KKT point stable uniform over all admissible tracker initialization. So this is the main global convergence. We apply the Lassale invariant principle on the compact positively invariant sublevel set, the set where the function derivative vanishes from the entire residue to be 0, which is precisely to the KKT. Lassale then gives that the distance from the trajectory to the KKT set go to the 0 when the time go to the infinity. The next slide is explicit parameter. From the above, we have to see that we have a more coefficient parameter to compute, and this is a closed form that we can compute directly. Next part is experiment section. We have the experiment to present in this our talk. The first one is Fat Valley SCP, and the second one is Arrow LMI SCP, and the last one is quantum tomography spectrograph. So the all of experiment we setting the our parameter like this. Okay. The slide is first experiment. The first benchmark is 2-dimension SCP with a 3x3 LMI. The optimal set is the entire line set, not a single value. So it is not a optimal. The optimal value is some 2 point plus is equal to 1. So making it a useful test for whenever the adaptive dynamics find the optimal manifold later than just a local minimizer. The left part shows that the phase span of 20 initial points or trajectory are attached to the different points in the red optimal manifold. It's not a go to the same point. I mean this is going to the point which nearest the starting point. The right part shows the primal coordinate converging to the complementary values summing to 1. Okay. Next is Fat Valley result. After we run 20 runs, successfully trigger the prescribed objective tolerance, the square distance to the optimal manifold is consistent with the objective accuracy. The most importantly, zero constant violation and zero PSD violation across all runs. The mean terminal time is well inside integration horizon, confirming that the method converges rapidly from the all test starting point. So the next experiment is called Arrow LMI SCP. The second benchmark is a 4-dimension SCP with an arrow structural 4x4 LMI and 3 nonlinear inequality constraints. The reference point KKT sits in nearly the boundary of the positive semi-definite cone, making this a genius difficult feasibility problem. Both phase span projection show consistent attraction toward the reference solution from all 20 initial points, despite very different from starting location. The result for the experiment 2 Arrow AMI is that the left panel confirms a monotone declare of composite Lyapunov function exactly as predicted by theorem 2 is decreased to 0. The right panel shows the square KKT error decay over time. An important lesson from this line with stop rule was based on a distance to the reference solution, yet the largest PSD residue at termination was still on the order of 10 to the minus 3. Distance to the KKT point is not the same as full KKT feasibility. In practice, both must be reported. So, the final experiment is quantum tomography. The third experiment comes from the quantum information. Give a noisy linear inversion estimate of 2-qubit density metric. We project it onto spectrograph. Spectrograph this means the set of x by x symmetric positive semi-definite metric with trace is 1. I mean the sum of diagonal element is 1. By solving a least square SCP with a 36 primal variable. Both plots show the practical decay, the objective gap, and the Frobenius reconstruction error accord of 5 initialization. So this is the density heat map. Tell the story. Visualization on the left is a noisy estimate which can have the negative eigenvalue in the blue, negative in the blue, and quantitativity track violation is most 1.7 times 10 to the minus 5. The minimum eigenvalue remain positive and the Fibonacci reconstruction error is approximate 2 times 10 to minus 4. The reconstruction methods are physical admissible, so I have a animation to see easier well what how the so at the first we have this is the last in the frame of 60. That means the our continuous time is go to final. We have the area of blue is disappear, and we just have a area of the red. That means this is a positive semi-definite visualization. So in a summarize and conclusion. So let me summarize the four main contributions. For the AMS GNS model itself, a continuous time gradient neural network with an AMS grad monotone envelope diagonal precondition designed for convex SCP. And second, the composite Lyapunov function that simultaneously capture the KKT geometric and the adaptive metric growth. Third, the provable guarantee that global extent Lyapunov stability uniform over tracker initialization and convergence of the KKT were Lazare invariant principle with a square integrable residual dissipation. Finally, fourth, explicit tuning of parameter bound is closed form and can computation, no hidden constraint. So this is the further work we may extend our continuous ODE to the nonlinear SDP where the LMI map may not have file. So thank you for everyone. Thank you very much for your attention. I'm happy to talk, take a question in the online YouTube if you have. So you can contact me with this email. So thank you very much.